Hello and welcome back to Calculus 1 section 4.6 on linearization and differentials. What we have here is an ancient section, something that we learned today to basically honor our ancestors, because today we have calculators and computers to compute things for us. But just like 70 years ago, you didn't even have a calculator. Like they started like 50 years ago, calculators with computers like 30 years ago. So it's very interesting to ask like a 5-year-old or 6-year-old what do they think was used like 40 years ago to compute, because they have no clue, right? They grew up with screens and all of these things. And, just thinking about it, that, the laptops are like not even 30 years, and the cell phones in the form we have today are not even like 15 years old, and so on. Um, Calculus is about 400 years old, and you have the algebra and all of these prior mathematics from 1500s. So it's not, too old. I mean, some of the concepts date back to ancient Greece and all of these other old ancient civilizations. But the real like heavy duty computation and then including the functions, um, some people are shocked when I say, well, you already know more calculus than Newton, right? Because Newton was able to differentiate polynomial, and that was it, right? Technically. You can differentiate exponential function. Exponential function didn't exist when Newton was around. How about that? Huh? Yeah. So, think about these things. So, what is this section about? This section is about computing, approximating values rather than computing them exactly. See, if I want to find, let's say, square root of 15, well, I immediately reach my calculator, I punch these numbers in, the decimals come up, I write the decimal answer, and I move along. Now, what if, and here I'm going to paint the picture, you're on a desert island, the battery on the cell phone ran out, the battery in your TI calculator that you always have with yourself, obviously in vacation as well, ran out, Wilson is gone, you have nothing to do, and all of a sudden, you just want to compute the value of square root of 15. This section is crucial for something like that. So let's go and discover how to find these values when when we are on that type of a desert island and so on. So now we can't compute square root of 15 in any quote unquote normal way, but we do know that the square root of 16 is 4, and we also know that square root of 9 is 3, and that this square root of 15 fits in between, so it has to be 3.9 something, right? 3.8 something, whatever it is, but it's closer to 16 than to 9, so maybe 3.8, maybe 3.9, but it's in there somewhere. And see, that is your, what you would call, educated guess, which is okay, right? But with linearization, we can actually come up with insanely close value with cheap calculation. Now, I'm going to explain that graphically first. So I can draw, x, the square root of x function, but we can also draw any other function. So yeah, right? And let's say that you want to compute a value right here, value C. No, sorry, value A. So you are interested at how much this point over here is A, f of A. So you are interested in how much the function value is. Now the problem is that the day is, let's say, 15, and it's a square root of 15, or it's ln 15, or e to the 1/2, stuff like that. Like, so you're looking at this and say, if I find the tangent line at the convenient point to compute, that it's as close as possible, then that tangent line will align itself nicely, trying to draw, there we go, tangent line. And this tangent line is computed at, oh, actually, no, tangent line is supposed to be A. I was right to put C there. Holy nightmare. There we go. I'm going to pwn this, and I'm just going to say nice value, which makes C a not nice value. So we found the tangent line at the nice value. Now, nice value is the one that you can compute without a calculator, like ln e, that's 1. ln e squared is 2. ln e to the 10 is 10, right? So those are nice value. Or ln 1 over e, well, that's -1, right? So those are nice value. Or square root of 81, that's 9. So for every function that you are trying to compute something for, trig functions like pi over 4, pi over 6, blah, blah, blah. So for every function, you always have this, what we would call nice values, where you can do your calculation without use of calculator. And now, when I have the equation of the tangent line, as you can see over here, because I really have to zoom in the most I can, I hope you see that the y value of the tangent line and the y value where the black point is for the original function is pretty much the same value. They're very close. Now remember, tangent line is y equal mx plus b. So I'm going to plug that 15 not in a square root, but I'm going to plug that 15 into my tangent line and make it this. So let's go. Let's do that. Let's do that. So I'm going to start my problem. Oh, by the way, linearization is get the tangent line. So hopefully you already picked that up from the example I gave with the picture. All right, so let's go. What? My voice just cracked. Okay, let's go. There we go. I need to sound menacing over here. Square root of 15 is equal to what? Okay, my function is root 15. And I'm going to find the tangent line at a equals 16. That's the closest, quotation mark, nice number for a square root. The other ones are 9 and 36 and 100 and 225. We have a lot of numbers that are perfect squares, and the square root would be a whole number when you do the square root. But 16 is, out of all of those nice numbers, 16 is the closest. So I am going to use tangent line at 16. Now we know the drill. For tangent line, get the slope, like all of that stuff. So let's start with the derivative. Oh my God, function is root of x. So derivative of root x is 1 over 2 root x. Slope is the derivative computed at what we called a nice value, because that's where we're computing our value. That's going to be f prime 16, which is 1 over 2 root 16, which is 1 over 8 in my case, because square root of 16 is 4. 4 times 2 is 8. And I also need a y value, which is the original function computed at 16, which would be square root of 16, which is 4. And that gives me 16, 4 as a point. And now place all of that into y equal mx plus b and get your tangent line. Y is 4. Slope is 1 over 8. X is 16 plus b. These two cancels to 9. So 8 cancels to 2. 2 times, so b is 2. There we go. What's going on over here? Oh, ink to shape. There we go. Ink to shape. I was like wondering, why is this all getting weird? All right. So now I have b is 2, and my tangent line at x equals a, which is whatever, or a equals 16, whatever, is going to be given by y equals 1 over 8x plus 2. Okay, here's the $1 million step. Square root of 15 is approximated by L of 15. Now, this is your L, because this is a linear function. We'll define it very soon as L. So, that's 1 over 8 times 15 plus 2. See? And now you don't need your calculator to compute this, because you should be able, to, use the stick in the sand, all right, and compute this without the calculator. So 8 into 15, right? And then you just add the 2. So 8 into 15 goes once, gives you 8, subtract 7, put 70, you get a decimal point there. 8 into 70 goes 8 times. 8 times 8 is 64, gives you a 6, put a 0, right? Depends on how many decimals you want to go for. So 8 into 60 goes 7 times. That gives you 56. It gives you 4, 45, 875. So 1.875 plus 2 tells you that the square root of 15 is approximated by 3.875. So we were able to compute this. Now I'm going to punch the square root of 15 in a calculator and tell you that the calculator value for square root of 15 is approximated at 3.87298. I'm like, really? The third decimal is a problem, right? So there is no scenario on the desert island when you are going to need this type of a precision, right, to build your hat made out of palm, right, trees or whatever else. So I can see you calculating square root of 15 at the desert island easily, right? Maybe you want to involve some elliptical, patio and things like that. Like, you have a lot of time, obviously. So sure, square root of 15 is gonna probably come up. That's not an issue. But the issue is that you don't really need all this precision, right? And you see that the procedure that we used, that we never used the calculator for, gave us a number that is so close to the quotation marks actual number, because this is decimals forever, that we don't really need to have the calculator. Now we can improve on this formula in Calc 2, and you have to wait for that when we improve on this formula. But for now, it's only going to be the linear calculation. So what we learned now is that your tangent line y equal mx plus b is actually your linearization. L of x equals mx plus b. And this is going to be now used to compute your values instead of using the calculator.
Hey, Professor, is that long division?
Yeah, this was long division of numbers. I was just messing around because I wanted to, keep that desert island thing going where you use the stick in the sand to do the division. I
Okay.
could have taken the calculator to divide this, get this number, and add 2, but I am pretending that I don't have it. So I'm going to do the same thing with the next problem as well. And the next problem is to compute. Let's compute ln of 15. Why not? ln of 15. Again, you are at the desert island and you say, okay, so what is the nicest value that I can pick, the closest value that I can pick for this to work? Because, right, I don't know, like what values are the closest to 15. I mean, we can put, let's put 18. Let's put 18. Okay, so now what should we do? Let's say we want to calculate this. This is a new problem. All right, so you go the nice value. These are the quotation marks. You can't see me do that, but quotation marks. The nice value is e and powers of e. Because if I have like ln of e to the 6th power, let's say, that's 6 ln e, and ln e is 1, so the whole thing is just 6. Ln e will always be 1. So whatever the exponent is, that exponent jumps in front, and that's just the answer for the whole thing. So I know that I want some kind of, when I'm looking for that a, right, to find the tangent line at, I'm looking for a to be of the form e to some power p. Now, what power p? Well, that depends on the number over here. So let's go and try and figure out what would the best power p be on it. So e is approximately 2.7. It's in forever decimal, right? It's not 2.7, but 2.7 is good enough. E squared is 2.7 times 2.7. So why I just say 3 times 3 is 9, so this should be something like 8. I don't care exactly. No one cares exactly. It's going to be somewhere around 8. You know what? Just for the hell of it, I'm going to punch in the calculator e squared. You get 7.389, like 7.4. Yeah, it's good enough. All right. E cubed. Well, e cubed is 2.7 times 2.7 times 2.7. That's like 3 times 3 times 3, that's 27. But that's really, if you have 2.7 and you approximate that as a 3 cubed, you have that as 27. But if you approximate this as 2.5 cubed, then you are getting what? Uh, 625 times 2.5, that's going to be 12. It's going to be in the neighborhood of around 15. Ooh. It looks like that if I use e cubed, the value is somewhat around 18. I don't know exactly how. It could be 16, could be 20, could be 21. I don't know. But it's that order of magnitude. So e cubed sounds like a good value to use, just because, right, the single e is about 3, this one is about 9, this one is about 20, and then e to the 4, right, would be about 64, because that's this one squared, right? So that should be common sense. So 18 should land somewhere around e cubed. Again, guys, I don't have calculator to check any of these things. I'm on a desert island over here. writing with a stick in the sand. So I figured out that I should use e cubed as the nice value for my tangent line. Okay, so let's go and figure out everything else. Again, if you missed any of this stuff, just go back to YouTube, watch this 15 times, you got it. And my f of x is ln x. That's my function, because I'm looking for ln of 18. The derivative is 1 over x, which means immediately that the slope is the derivative computed at value a, and that is 1 over e cubed. Okay, that sounds good to me. So now I need to compute my y, and the y is going to be ln of e cubed, which is 3. So what are my specs for tangent line? I have a point, e cubed 3, and I have the slope of 1 over e cubed. So y equal mx plus b, y is 3, m is 1 over e cubed, x is e cubed plus b. These guys cancel, and that gives me that b is 2. So my linearization formula, now instead of y, I'm going to put L of x, because we just learned that, right? We just learned that. So instead of writing y equal mx plus b, I'm going to put Lx, right, which is the linearization, which it approximates, is going to be 1 over e cubed times x plus 2. Now, it's good time for me to now invest time into multiplying this against stick and a sand to just see what this equals to without the calculator. Now, before you run in terror, it's a simple calculation, guys. It's going to be 1 over 2.7 cubed. That's good enough. That's good enough, right? So I have 2.7 times 2.7. Here is me in the right stick in the sand. So 7 times 7 is 49, and then this is 18. Placeholder, 2 times 7 is 14, 4 and 1 is 5. Add them all together, 9 to 7 times 2. I mean, so 2 decimal places. And now times 2.7. So we do it again. So we do one more multiplication now. 7 times 9 is 63. 7 times 2 is 14 and 6 is 20. 7 times 7, 49, this is 51. Put the 0, placeholder. 2 times 9 is 18. 2 times 2 is 4 and 1 is 5. 2 times 7 is 14. 3, 8, 6, 9, 1. 3 decimal places. And since I am undershooting here, I'm just going to round this to 20. The reason why I'm rounding this to 20 is because each one of these 2.7s was supposed to be more than 2.7. So I'm just going to round this up to an even 20 and call this L of x equals now 1 over 20, right? Now, how much is 1 over 20? It's 0.05x plus 2. There you go. I mean, we can leave 1 over 20. It's like pick your poison, right? But 1 over 20 is a good value, right? You can leave it as a fraction or you can leave it as a decimal. You are at the desert island. You own the whole thing. You're the boss. You pick whatever you want, right? So now we're going back to ln of 18. Well, ln of 18 is approximately L of 18, which now is a joke. I'll leave this as 1 over 20 because now it's easier if it's fraction than, shoveling the decimals. So ln 18 is approximated by 18 over 20 plus 2. Now 18 over 20, I can cancel that by 2 and get 9 over 10. And that's 0.9 plus 2, it's 2.9. So my calculation here says that ln of 18 is approximately 2.9. Now, what's the first thing that you're going to do when you get rescued from this desert island? Right? So you are on this ship, right? Dehydrated, hungry, angry, depressed, and all of that stuff. The first thing you do is you ask for the calculator, obviously, to check your ln 18 calculation. And it comes out ln 18 is 2.89037 blah 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 blah. Yeah, you're like 1 cent off with doing all of that stuff in the sand. So these calculations, guys, are really precise. They can be made much better, and we will make them much better in Calc 2. For those of you going to Calc 2, you will see that in Chapter 11. But for right now, with knowledge that we can make this even better, this is already pretty damn good, right? Our values that we are computing without a use of calculator whatsoever are already very, very close to the values that the calculator gives. Now, we understand that these are approximations. Now, what happens when you pick this value poorly? When you pick this value far away from the value you are trying to compute, your entire calculation becomes garbage, because the further away you are, right, from the point you are trying to compute, the more error there is when the tangent line is done. So let's say you want to calculate, let's say you pick this, right, because that was number 1, and number 1 is easy to compute, and you do the tangent line there. Look at the difference in the y value when you compute your c in a tangent line. There is a lot more distance there than what you have, right? You could have picked it, let's say here, right? That will give you the tangent line that looks like this, actually more slanted, with tangent line that looks like that. Look at the difference now in error with the calculation. You cannot pick a number that is far away from the value you want to compute, because you will get the wrong answer every single time. They're not going to have anything even remotely close. But when you pick them to be very close to each other, like we did here between A and C, then look at that. You do not have too much of that vertical change there, and it's very, very close. Cool. So we use linearization to approximate value of the function. That's what we use linearization for. And again, unfortunately today, well, fortunately or unfortunately, whichever way you want to look at it, we don't need this today anymore, because you can just immediately grab your cell phone, right, and punch in ln 18, get your answer of whatever it was, 2.89, and move along. And as I said, this is why this is a section where we honor our ancestors, right? Now, there is a formula that you can write which will give you the whole thing in one line, and that's the one they presented in the book. At the end, all of this entire section is just nothing more but a tangent line calculation at the point that you pick, and you have to be smart enough to pick that point to be very close to the point you're trying to compute, or to the point that you're trying to approximate. All right. I hope you remember y minus y1 equals mx minus x1. This was called the point slope formula for equation of the line given to you in algebra course. Okay, so now we can see these other values like x1 and y1 at work, and those are the values that you pick, and we can rename this formula. So we start with x1 is the a. That's the value that you pick. Now that immediately means that y1 is f of x1, which is in turn f of a. And finally, we know that the slope is f prime of a. Well, I hope you see that everything depends on you picking the value correctly. So if you pick a terrible point, the whole thing immediately is wrong. So now what do I have? I have y minus f of a is equal to f prime of a times x minus a. And you just move this to the other side, and you get your, and you call your y L of x. So here is your linearization formula. L of x is equal to, this f of a is kicked to the other side, so we have f of a plus f prime of a x minus a. This is your linearization. Which is technically tangent line in one formula. So when you have a problem, next time they give you some kind of f of x, 1 over x plus 3, whatever, and they want to compute f of, I don't know, x, so f of, it doesn't really matter, 3.6, whatever, right? You pick a equals to 4 because that's easier to compute, and you just immediately plug everything everywhere, right? You have your f of 4, and that's going to go there. You have your f prime of 4, that's going to go here, and you're going to have your x minus 4, which is this parenthesis here. It's instant. As soon as you pick this, these three parts go into the formula, and you're done. These problems, when you practice, I mean, they shouldn't take longer than, 2-3 minutes each. It's a really quick thing. So I hope you guys will try that on the homework. And then if you have questions and problems with it, you will stop by and ask. The second part of this lecture is differentials. Now, differentials approximate the change. Differentials approximate the change. So when you are using linearization, you are approximating the value of the function. You're approximating the number, the value. When you are approximating, when using differentials, you are approximating the change. Now, what change? Again, something that we really don't need anymore because we have computers, but it's kind of a cool thing to know. So let's say that you have a spherical balloon, for instance, right? The spherical balloon, I don't know how much of a sphere that is, but whatever. Spherical balloon. Then just put a little bit more air in it. Radius grows and the whole balloon becomes a little bit bigger. So your radius went from R1 state into R2 state. Whether it became larger or smaller, I don't care, but for our purposes, we added a little bit extra air, so it became larger. Now, as a consequence of that, immediately volume went from volume 1 to volume 2. So now, change in volume is delta V, and that is V2 minus V1. And that is something that with the calculator you can compute quickly, right? But remember, it has a cube in it, and it has all of these calculations with pi 3.14. So yeah, not too cool for people without a calculator. Let's say a Rutgers student, right? Rutgers students and NGIT students, they're students with no calculator. So let's go and compute the approximate change, because this would be exact change, because I am using the actual R1 and R2 in the formula to compute V1 and V2. We know that the formula for sphere is 4/3 pi r cubed. You compute that for the larger radius, then you compute the same formula for the smaller radius. You subtract the two numbers, you get your exact change, because the volume of the balloon changed from V1 to V2 because we added extra air. But in general, it's too much calculations, right? It's too annoying. So is there a better way? And the answer is yes, differentials, which is why we're learning them. Now, to derive differentials, you start by saying y equals f of x. And then when you differentiate this, you write the Leibniz notation on one side and that modified Newton on the other. And you simply move this dx to the other side. So what you get is that the dy is equal to f prime of x dx. And I'm going to just change one thing here, and that is to write dy is equal to f prime of x delta x. This is your differential. Now, there are certain things that you need to note. Delta x is the same as dx, and that's x2 minus x1. Delta y is not the same as dy, which is y2 minus y1. This is y2 minus y1. But they're close, which is why we say that dy approximates the change in y. So we want to know change in y. change in profit. Am I making profits or I'm losing profits? Right? Change in volume. Volume goes up, volume goes down. By how much? Because when you subtract through volumes, you get the difference is how much the volume grew. So we get to calculate a lot of stuff. We get to calculate a lot of stuff here. And maybe the differential up there would be very quick for us to use rather than to calculate the exact change. You can just approximate. So dy is approximately equal to delta y. And then you can avoid, calculating these formulas twice and so on. Again, not a big deal today. You have calculators and everything else. But in the good old days, yes, it was really annoying. So now, can we use this to calculate root 15? And the answer is yes. Now you might say, but hold on, professor, you said that this is not approximating values of the numbers. This is approximating the change. And I'm going to say yes, very good, you're paying attention. I can use it to indirectly compute this because I'm going to pick my A to be 16. Now, do you see how the input number changed from 15 to 16? And since there is that change there, that will trigger the change in y. So I can just compute the root 16 and subtract the change, and I will get the approximation for root 15. But let's get there. So if I want to compute root 15 using a differential method, then I just say, oh, let me pick the easy value, and then I'm going to compute dx. And dx is always given by new minus old. So what I have here is that delta x is equal to, and I'm going to have it as 16 minus 15, which would be 1. And now I'm going to get the function. That function is clearly root x because life, right? Has to match the function. And now you have the formula which said dy is equal to the f prime of x delta x. Well, I already know what delta x is. I clearly need the derivative here, so we'll take care of that, which is 1 over 2 root x. And now we plug everything in. So dy is equal to, that goes there. We get 1 over 2 square root of 16. And then this one is the 1. So the whole thing is 1 over 8. So that's the change in this one. Okay, so what is square root of 15? Use some common sense. It's going to be square root of 16, take away the change. Because when I changed my input number from 15 to 16, the output changes, and I can detect that change in output by using the dy, approximating dy. So this becomes 4 minus 1 over 8. And that is 4 minus 0.125, I believe, which is 3.875. Now, we did, I think, do the calculator earlier. 3872. 3872. It was like 9, 8, blah, blah, blah. Again, off on the third decimal. So you can actually use differentials. I want to say calculator there. There we go. So we can use differentials to still calculate values, but we are now doing it differently. Right? With linearization, you approximate the number you want directly. But over here, you actually calculate the difference between the two x values first, and that's the difference between the value they want you to compute and the value that you picked as easy to compute. So that's the difference between 15 and 16, which is what I captured here, and you get your delta x to be 1. And then, right, we unleash the differential formula, we compute the change. Once I have the change, it's game over, because root 15 is the one that it's easy to compute for me, and then obviously I need to subtract, in this case, 1/8, because I need to go down with this value, because 15 is smaller than 16, so root 16 will give a bigger value than root 15, so I need to come down a little bit towards the root 15. So that's why we subtract this value. Sometimes you're going to add, depends on the problem. Again, it's all about the common sense. So let's take a look at the problem in the book using differentials. Now, ln 1 minus x. Yeah, why not? So problem 70 says y equals ln of 1 minus x. Oh, that's a problem. Now, they don't give us a value to compute. They just want us to compute the differential. And then we can argue the difference in between what the differential gave us and what we computed. But let's start at our good old friend, the derivative, which is 1 over negative 1 over this. You write the function as is in denominator and put its derivative on top. That was the way we took the derivatives of ln. Now, when you do that, you can also write this as 1 over x minus 1, because that negative can be distributed in the denominator and just change both signs and then just swap the order. All right, so the problem says, consider the following functions and express the relationship between a small change in x and the corresponding change in y in the form of the y. Okay, so a small change in x. That means that this x is going to grow a little bit. So let's call x changes into x1, which means that my delta x is actually x1 minus x. Now, there is actually a nice way to do this. I should offer money at this point and say, okay, so how did we added a small value at some point earlier in calculus? Like, how did we add a small value? Don't remember it, huh? It was the a plus h in the derivative definition and all of that. So we can say x goes to x1 and do the problem this way, or we can say that x1 minus x is equal to that age, and then you can drag that through the calculation. So whatever makes you happy. Now we have our f prime. Now f prime needs to be computed at x1, and that's just 1 over x1 minus 1. Easy. And here's the change in y. So the change in y is given by the derivative, which is this, times the difference with these two. So technically dy is x1 minus x over x1 minus 1. So that's the change. Now let's calculate the exact change. Exact change was ln of 1 minus x1 minus ln, no, this is supposed to be x minus. The new minus, then the new one is when you move to, so new one minus the old one. Yeah. Now we know that these guys stack. Wait. Yeah, they stack on top of each other. So I just have the ln of 1 minus x1 over 1 minus x. So I hope you appreciate the fact that this is much easier to compute, because at this point x1 and x are just numbers, but you still have to take the ln of that if you are doing the exact way versus approximation way. So in approximation, when you know what these values are, just plug them in and you get the answer immediately. Here, you actually have to use a calculator to come up with the ln values. So we were comparing. Just change this because I'm used to. So it says, how does it compare? That was the question. How does it compare between the approximation and the exact calculation? Well, you see that the exact calculation still has the ln floating about, making it much harder to compute, where our approximation just has x and x1, you plug them in where they belong, and you're literally done in 10 seconds. Now, differentials can explain a lot more as you go through homework. I hope that you're going to find all of them. Now, what I want to point out is that this one really cool problem that reminded me of, situation when you drive in the summer and there's a lot of exploded tires on the road. Like, you can follow the change um, looking into differentials or whatever, but you can follow the change and you can find trying to word this differently so it's not confusing. When you have, let me write, okay, let's have something to look at. Much better. So when you are, like, I'm talking about the tire debris on highway and all of that stuff. So why is it so much more in summer than the winter or any other time in the year? So ideal gas law is the pressure times volume is nR times the temperature. That's your ideal gas law. Now this is a constant. You can call it equal to 1 and then you just don't have to worry about it. Now the volume of the tire is somehow fixed. because the tire, once you inflate it to the point, right, it has the maximum pressure that it can hold, and if you put more air, it will explode, right? So you can think of the volume of the tire to be constant because, I mean, you know, it's inflated all the way and there's no more room for expansion. Now, those tires are also rated for a certain amount of PSI of the pressure. And if you go with pressure to more than what the tire can withstand, the tire will explode. Now, on the other side of the equation, when you ignore these constants, you have temperature. So now, what do we know in the summer? What you know in the summer is that your tires are not just warm because of the contact with the road where it creates the friction so your car can go. It's not just that. It's also added heat from being summer. You know, sometimes in the summer you have 100 degrees weather. Right? You go to Arizona, it's 200 degrees apparently. Like people don't even use pools there. It's like, forget it. I mean, you can use it to boil eggs. So when you have the extreme temperature and the temperature goes up, then this side collectively has to go up. But being that, right, that the volume is somewhat fixed because the tire can't expand anymore because it's expanded to all the way, the pressure goes up. And the tire explodes. Which is why it's recommended to lower the tire pressure in the summer, right? So you follow these rules because some engineer computed the differential for it, figured out what is the change in pressure in regards to the change of temperature, right? By how much it's changed. And you don't need the exact number to 15 decimals, so you do all of this stuff. Like differentials would work just fine. But again, I just want to connect this into, you know, an application because at some point somewhere someone said, all right, your tire is rated for 51 psi. Oh, summer rolled around, put 36 in your tire. And then, you know, winter rolls around, put 40 or 42. Your tire is rated at 51 psi. Like, and then you put the tire that is rated at 51 at 51, and then you wonder within 30 minutes why a tire exploded, right? If it's summer, well, you already went to the absolute maximum, and then the heat just made it expand more, but it couldn't, and it exploded, right? So this is where, right, the knowledge, right, kicks in, and you can make good life decisions, right, and not just go with, you know, that defiant behavior immediately. Oh, no one's gonna tell me what I'm going to do. Well, right, it's not fun to have a tire explode on you when you are on the highway driving 70 or whatever. Um, let's take a look at one word problem for differentials. And oh, it's 5:15. Don't have time for okay. Well, next class. Next class is going to be probably just one section. It's long, so we're gonna do like the break in between and all that. Okay, let's see what we have here. Cylinder. I did. If you are interested in this uh, problem with approximate the change the atmospheric pressure, blah blah blah. 56. I actually did it in the other class. So if you watch, like on Saturday, so if you watch the Calculus 1S streams, you will see problem 56 done. Now for you guys, I'm going to take a look at this right circular cone. I never did this. All right, so we have a cone where the radius is fixed at 20 centimeters. When its height decreases from 12 centimeters, so 12 centimeters to 11.9 centimeters. approximate the stuff. Oh, this is not a cone problem. This is a cylinder problem. The, I was looking at two problems at the same time, reading a little bit from one and a little bit from the other. So let me sort this out. So problem 57 is the cylinder, radius is 20, that's good. Height is decreasing. All right, good. So I just picked up the cone from 58 and then did the rest from 57. Okay, it's a cylinder, not the cone, cylinder. All right, so we know what the volume for this thing is, right? Area of the base, which is pi r squared times the height. And being that the radius is fixed, you can immediately have this at 400 pi h. Now, this is your function in terms of the height. And you can differentiate that. And you can also calculate your delta h as nu minus old. Now that's a negative value. Well, if the height is diminishing and the object is of the same width, obviously we're going to have a decrease in volume because of that. So the change in volume, actually let's do it this way. The change in volume is approximated by dV, and dV is V prime times delta H. So 400 pi times negative 0.1, and that's going to just make it negative 40 pi. Now pi is about 3, so negative 120, a little bit more than that and all that kind of stuff, but no one cares. So negative 40 pi. So as the centimeters cubed. So as the height is decreasing, the volume is decreasing as well, and there you have it. So that's it. A section on approximations. As I said, ancient history, right? For us now that we have ways to compute this without going through all of these hoops. But at some point, in 1874, someone needed ln3 for a calculation and did not have a calculator to find it. So they had to be clever, right? They had to be clever, and they had to be they had to know how to find these values and the other way. Okay, so the next class is going to be the section, very important section on L'Hopital's rule, which is limits, finding limits using derivatives. And it's one of the very important sections for Calc 2. You get to suffer in 2 chapters if you don't know 4-7. So don't play with fire. Make sure you are mentally present at all times on Wednesday, and participate, ask questions as much as you can. Fix my mistakes, obviously. Pay attention. And yeah, so I will see you all on Wednesday, 2 days. Bye.